Now we'll see the relations between Kp and Kc. Already I said you that is Kp is equal to partial pressure of the product by partial pressure of the reactant, and Kc is the concentration of the product by concentration of the reactant. What is Kp? Kp is equilibrium constant at a given pressure. And what is Kc? Kc is equilibrium constant at a given concentration. Okay, fine. We will find the relations between them. Now when we will find the relationship, Kp and Kc, they are what you can say constant. That is equilibrium constant at a given concentration, given pressure. That means it is under standard conditions. So when we talk about standard conditions, then definitely the ideal gas law comes into our mind. So same reaction I will take XA, a reaction, an equilibrium reaction I am taking it to find the relations between Kp and Kc. I am taking a reaction XA plus YB gives ZC plus WD. We can say that. So in this particular reaction, A, B, C, D are the reactant and the product, and X, Y, Z, W are the number of moles of the reactant and the product. Okay, fine. Now according to the ideal gas, PV is equal to nRT. So P is equal to N by V RT, and N by V is what? Concentration, that is C. Concentration, that is C. N by V, number of moles by volume is your concentration, that is C. Fine. Now next is for the partial pressure of A. For the reactant A, we will find the partial pressure of A. It will be concentration of A. This is your concentration of A into RT. Now, how many moles of A is there? X moles of A is there. X moles. So, we will take partial pressure A to the power X. So, this also to the power X and this also to the power X. Definitely. Fine. Similarly, for the partial pressure of B to the power Y, it will be nothing but concentration of B to the power Y into RT to the power Y. I hope you understood this, the first one. Same thing we'll do for the C and D also. Partial pressure of C to the power W is equal to concentration of C to the power W into RT to the power W. Then partial pressure of what you can say, not C to the power W, it is C to the power Z. Yeah. So it will be concentration of C to the power Z into RT to the power Z. Yes. Now next is partial pressure of D to the power W. This is W. Then concentration of D to the power W into RT to the power W. Fine. Now we will use this particular value, as you can see it here. I have written the value. I will be using this particular value in the equation. That is Kp is equal to, what is that? Partial pressure of, what is the formula? Partial pressure of that is C to the power Z into partial pressure of D to the power W, because I said you it is the partial pressure of the product by partial pressure of the reactant by partial pressure of A to the power X into partial pressure of B to the power Y. Okay, now we'll put the value now. Partial pressure of C to the power Z is how much? See here, partial pressure C to the power Z is concentration to the power Z into RT to the power Z. D to the power W is this, A to the power X is this, B to the power Y is this. I am going to put the value there. Got it. So what is that? Concentration of C to the power Z into RT to the power Z into this one, concentration of D to the power W into RT to the power W by concentration of A to the power X into RT to the power X into concentration of B to the power Y into RT to the power Y. I have put the value now. After putting the value, what we will do is that we will now just simplify it. Now I can write in this way, C to the power Z into D to the power W by A to the power X into B to the power Y into RT to the power Z plus W minus X plus Y. See here, Z plus W minus X plus Y. Why it is X plus Y? This is nothing but number of moles of the product. Z plus W is. And X plus Y is the number of moles of the reactant. That is what I have written. Now what is this? This one is what? Kc, isn't it? So this is what? RT. What I said, Z plus W is the number of moles of the product and X plus Y is the number of moles of the reactant. So I can write NP minus NR, number of moles of the product minus number of moles of the reactant. So Kp is equal to what we got it ultimately, that is Kc into RT to the power Np minus Nr is what? Delta Ng. What is G stands for? Number of moles of gas. We are, because when will I subtract the number of moles of product and reactant, I will be taking only the gaseous substances, not for the solid and liquid. Alright, not for the solid and liquid, because change in number of moles of solid and liquid is quite negligible. We can say that. In case of gas only we are getting it. Substantial value, we can say that. So hence we got the relationship Kp is equal to Kc into RT to the power delta Ng. This is a very important relationship. This one is Kp is equal to Kc into RT to the power delta Ng. Generally the value of R we take it as 0.0821 liter atm per Kelvin per mole. Alright, we take it as, where pressure is in atm and volume is in liter, temperature is in Kelvin. But if the pressure is expressed in bar, mind it, we have read it already in the previous chapter, that is states of matter. Then if the pressure is expressed in bar, then the value of R will be 0.0831 liter bar per Kelvin per mole. 0.0831. Alright, and the relationship between bar and Pascal is that 1 bar is 10 to the power 5 Pascal, you know it. And 1 Pascal is 10 to the power 5 Pascal is nothing but 10 to the power 5 Newton per meter square, because 1 Pascal is 1 Newton per meter square, or we can say 0.987 atm. 1 bar is 0.987 atm. All these things you have studied in the previous chapter. You have studied all these things. We can say that. Now Kp and Kc can have 3 values definitely. From the relationship Kp is equal to Kc into RT to the power delta Ng, we can have 3 relationships. What is that? Either Kp will be equal to Kc, or Kp will be greater than Kc, or Kp will be less than Kc. Alright, if Kp is equal to Kc, see here, if Kp is equal to Kc, then delta Ng will be 0. Change in number of moles will be 0. Because anything to the power 0 is, RT to the power 0 will be what? 1. So hence Kp will be Kc. Alright, when it will be, that is, it will be 0, delta Ng will be 0, see that, H2 gas plus I2 gas gives 2Hi gas. In this case, delta Ng is equal to 0, because number of moles of the product is 2, number of moles of the reactant is 2. 2 minus 2 is 0. So here in this case, Kp is equal to Kc. You can put the value. Delta Ng 0 means RT to the power 0 is, anything to the power 0 is 1. Now, next is, if I write the reaction, PCl5 gas gives PCl3 gas plus Cl2 gas. Alright. Now here the number of moles of the product is 2, number of moles of the reactant is 1. See, I have written all gas, mind it. If anything will be solid or liquid, that will be taken to be as 0. We will not consider it, that particular one. Alright, we will not consider it. Alright, for example, see here, C solid plus O2 gas in this reaction. It is CO2 gas. This is C solid, carbon solid. So here the change in number of moles is, this is number of moles of product is 1, number of moles of the reactant is also 1. This I will not consider to calculate the change in number of moles, because it is a solid. So here 1 minus 1 is also 0. Delta Ng is also 0. Understood? So try to understand that. In case of solid and liquid, we are not considering it, because it is not compressible. Solid and liquid, hardly it is compressible. So here the delta Ng value is how much? It is 1. We can say that. So when delta Ng is 1, so Kp will be greater than Kc. We can say that in this. Now if I take N2 gas plus 3H2 gas, reversible sign gives 2NH3 gas. We can say that. Then delta Ng will be, this is number of moles of product is 2 moles and the reactant is 4 moles. You can see this is 1, this is 3, 4 moles. So 2 minus 4 is minus 2. So Kp will be, what is that? It will be less than Kc, because Kc into RT to the power minus, negative. So Kp will be less than Kc. So I gave you 3 equations, just 3 examples I should say, that I have given you when the Kp will be equal to Kc, when Kp will be greater than Kc, when Kp will be less than Kc. Because Kp and Kc can have 3 values. Either it can be greater than 1, either it can be less than 1, or it can be equal to 1, so to say. I hope you understood this. Now, that is the value of equilibrium constant depends upon certain factors. Alright, like equilibrium depends upon certain characteristics, certain factors. Similarly, equilibrium constant also depends upon certain factors. there are also certain characteristics of equilibrium constant, mind it, equilibrium constant. So what is that? The value of equilibrium constant for a particular reaction is always constant depending only upon the temperature of the reaction and independent of the concentration of the reactant with which we start the reaction, we can say, with which we start the reaction, or the direction from which the equilibrium is approached or equilibrium is attained. That means, in short, I should say, that is, equilibrium constant depends upon temperature. If temperature is increased, then equilibrium constant is increased. If temperature is decreased, equilibrium constant is also changed, we can say that. Because the numerical value of the equilibrium constant for a particular reaction is constant as long as the temperature is kept constant. Alright, as long as the temperature is kept constant, then the numerical value of equilibrium constant remains as constant. Alright, now if the reaction, if the temperature is changed, the rate of the reaction also changes. If the temperature changes, rate changes, and if the rate will change means what I said, Rf is equal to Rb at equilibrium. So if the rate will change, then definitely the reaction will not be in equilibrium. Then definitely the equilibrium constant is also going to change in that particular case. Clear? So hence, our equilibrium reaction, equilibrium constant depends upon temperature, increases or decreases with increase or decrease in temperature, so to say. But it is independent of the initial concentration of the reactant. Means it does not depend how much, with what value you have started the reaction. With the initial concentration is 1 mole, 5 mole, 2 mole, 4 moles. Or it does not depend upon that. And it also does not depend upon from which direction the equilibrium is attained. Equilibrium is attained from the forward direction, or it is equilibrium is attained from the backward direction. It also does not depend upon that. It only depends upon that the reaction should be in equilibrium. That's it. Whether it is attained from forward or backward, immaterial it is. Alright, this point you should remember. Now next is, if a reaction is reversed, the value of equilibrium constant is inversed. If a reaction is reversed, we can say that. That means, that is, let us say our reaction is there, PCl5 gas gives PCl3 gas plus Cl2 gas, so to say. So equilibrium constant Kc is what? Concentration of, I can say, PCl3 into concentration of Cl2 by concentration of PCl5, isn't it? This is equilibrium constant for this particular reaction. Now the reaction is reversed. That is, I will write PCl3 gas plus Cl2 gas gives PCl5 gas. Now the equilibrium constant, let us say I am writing K dash C, this one is. So K dash C is what? Concentration of PCl5 by concentration of PCl3 into concentration of Cl2. Now what is the relationship between this and this? You can see it here. It is the reciprocal of. So K dash C is equal to 1 by Kc. That is what I said. K dash C is equal to 1 by Kc, we can say. You can see it here. That is the reciprocal of each other. So for that reason I said, if a reaction is inversed, alright, then the equilibrium constant is also, if a reaction is reversed, alright, reversed it is, then the equilibrium constant is inverse. It is inverse of each other, we can say that. Now if an equation having equilibrium constant is divided by 2, alright, the equilibrium constant for the new equilibrium will be the square root of the original one. What I said, if the equation having an equilibrium constant, let us say K, alright, is divided by 2, the reaction is divided by 2, an equilibrium reaction, it's divided by 2 throughout, alright, then the equilibrium constant, the new equilibrium constant which will be formed is the square root of the original one. Let us say the new equilibrium constant is K dash, so K dash will be root over of K, we can say that. Clear? If this particular reaction, if I divide it by 2, alright, if this reaction, if I divide it by 2, then the new equilibrium constant which will be getting it, that is K dash, let us say, is equal to root over of K, K to the power half. That means if a reaction is divided by 2, then it will be the square root of the original one. If a reaction is divided by 3, it will be the cube root of the original one, cube root of original one. If a reaction is divided by 4, then it will be the fourth root of the original one. Similarly, if a reaction is divided by n is any number, then the reaction will be, the equilibrium constant will be, the new equilibrium constant will be the nth root of the original. Nth root means K dash is equal to K to the power 1 by n. That's it. Square root means what? 1 by 2. Cube root means what? 1 by 3. So nth root means what? 1 by n. So if a reaction is divided by n, any value, then the new equilibrium constant will be the nth root of the original one. We can say that. Similarly, if an equation is multiplied by 2, if an equilibrium reaction is multiplied, instead of dividing, multiplied by 2, the new equilibrium constant is the square of the original one. Suppose this equation I am multiplying throughout by 2, the new equilibrium constant which I will be getting, that is k dash, will be the square of the original one. So k dash will be k square, it will be the square. Similarly, if an equation is multiplied by 3, it will be the cube of the original one. If an equation is multiplied by n, then it will be the n, what you can say, to the power n of the original one. Means k dash is equal to k to the power n if it is multiplied by n throughout. We can say that. Similarly, if two equilibrium reaction is added, one is having equilibrium constant as k1, other is having equilibrium constant as k2. So the new equilibrium constant will be, that is, let us say k will be the nothing but product of the two equilibrium constant. Okay, let us say this equation is equilibrium constant is k1 and this equation equilibrium constant is k2. So when I add it, I will be getting a particular equation. So that equation will have equilibrium constant, let us say k. K will be product of k1 into k2. Any two equation, like in this equation, if you add it, it will get what you can say, that is, it will get subtract, cancelled. Everything is going to get cancelled. Suppose any two equations are there, two equations are there, you are adding the two equilibrium reaction. One equilibrium reaction is equilibrium constant is k1, other equilibrium reaction equilibrium constant is k2. If the two equation is added, we get a final equation, the third equation. So the third equation is equilibrium constant, if it is k, then k will be k1 not plus into k2. So if two equation is added, then the equilibrium constant is the product of the original one. Equilibrium constant is the product of the original one. We can say that. This you need to remember it. Alright, if it is divided by 2, it will be the square root of the original one. If it is multiplied by 2, then it will be the square of the original one. If it is added, then it will be the product of the original to equilibrium constant. We can say that. And if a reaction is reversed, then the equilibrium constant is inversed. Okay. Now the value of the equilibrium constant is not affected by the addition of catalyst to the reaction. If you add any catalyst, then what will happen? Will the equilibrium, what you can say, of the reaction change? No. So the equilibrium constant is not affected by the addition of catalyst. The only thing will happen is that if you take a catalyst, then the reaction will attain equilibrium at a faster rate. The only thing will happen is that the reaction will attain equilibrium at a faster rate. So equilibrium constant is not affected by the addition or removal of catalyst. It is not affected. Equilibrium constant, we can say that. So this you need to remember. We can say that. Now coming to the types of equilibrium, we are having homogeneous equilibrium and heterogeneous equilibrium. Homogeneous equilibrium means if the reactant, product and product are in the same state, then it is called as homogeneous equilibrium. You can see it here. The reactant and product are in the same state, all are gaseous. So this reaction is a homogeneous equilibrium. This reaction is a homogeneous equilibrium. But if I say this particular reaction CaCO3 solid, it will give you CaO solid plus CO2 gas. It is a heterogeneous equilibrium, we can say that, because the reactant and product are not in the same state. If the reactant and product are in the same state, then it is called as a homogeneous equilibrium. If the reactant and product are in different state, it is said to be as a heterogeneous equilibrium, so to say. We can say that. In this way, we write the, we determine the homogeneous and heterogeneous equilibrium, so to say. We can say that. Now, from the value of equilibrium constant, many more things we can find it out. Got it? We can also find the extent of the reaction. Now see, listen carefully. If the value of equilibrium constant, this is very large, the value is coming, let us say 1.2 into 10 to the power 35, let us say 1.2 into 10 to the power 35 or 2.5 into 10 to the power 50, the value, it's very large. That means what? When this value will be large, when this value will be small, listen carefully, when this will be large, this value will be large, when this will be smaller, isn't it? Concentration of this will be small or the concentration this will be large. So when this will be smaller, concentration of the reactant, this reactant is smaller, when the reaction has proceeded far towards completion, isn't it? When, see, if this is big means this has to be small. If this is big means this has to be small. This is what? This is a reactant. So if the reactant is used up almost completely, then only this will be smaller. Then only this will be bigger. We can say that if the reactant is used up, then only the product will be formed. Isn't it? So if the concentration of the reactant is decreasing, then the concentration of product will increase automatically. isn't it? So if this value is large, that means this value is small. That means the product is used up almost completely, we can say that. So hence what we can conclude, if the value of equilibrium constant is very, very large, is much, much greater than 1, then we can say that the reaction has attained far towards equilibrium. The reaction has proceeded far towards equilibrium, far towards completion, rather I should say, that's a better word. The reaction has proceeded far towards completion. That means the reaction has proceeded in the forward direction only. Forward it is going. It is moving in the forward direction, we can say that. Now if this value is small, means this value is large. If this is small, means this is large. That means when the value of equilibrium constant is small, that means the reactant is hardly used up. Hardly it is used up, because if this will be greater, when this will be greater, when the reactant is hardly used, that means the reaction is hardly proceeded in the forward direction. Means reactant is hardly used up, then only the product is little bit it is being found, because this value will be smaller. If this value is large, means this value is smaller, definitely, because they are related, na? So in this way, if this value is small, then this value will be large. But if this value is large, that means reactant is hardly used in the reaction, then only it will be large, because always concentration is means what? The one which is left out after the equilibrium is attained. So if hardly this reactant is used up, then only it will be left out in large quantities. So hence in that particular case you will find it out that this value will be very, very small. If this is bigger, then this is smaller. If this is smaller, means what do we conclude? We conclude that the reaction has hardly proceeded in the forward direction. Hardly proceed in the forward direction. But if the value of Kc is almost equal to 1, like it becomes 0.99 or 0.98, or sometimes we get 1 also. How will you get 1? When this by this cancels. The value of the product and the value of the reactant. When the concentration of the product and concentration of the reaction, if it is same, if it is equal, when it will be equal? Concentrated product and reactant, when it will be equal? When the reaction is in equilibrium. When the reaction is in equilibrium, then only the concentration of the product and the reactant will get cancelled. So when the reaction is in equilibrium, the value of Kc or Kp, that is equilibrium constant, will be equal to 1. Nearly equal to 1 or equal to 1, we can say that. So from the value of equilibrium constant, again I repeat, if the value of equilibrium constant is very, very large, if this value is large, that means the reaction is proceeded far towards completion. If this value is very, very small, the reaction is hardly proceeded in the forward direction. If this value is equal to 1, we can say that, then the reaction is in equilibrium. In this way, from the value of equilibrium constant, we can conclude this. Thank you.